going to look at something called sigma notation. It's a very handy notation when it comes to writing out a series in a very shorthand, compact kind of way. And let me show you what I'm talking about. Let's start off and look at what sigma notation actually is. What we have might look something like this. We have k equals 1 up to 5. These are called the lower and upper boundaries. And this is kind of the generator of each term. What we do is k starts at 1, so I have 2 times 1. That's my first term. Plus, then k is now bumped up to 2, and then I have 2 times 2. Plus, then k gets bumped up to 3, and I have 2 times 3. Plus, k gets bumped up to 4, 2 times 4, plus 2 times 5, and at 5 we end. So what I now have is a series that looks like this. 2 plus 4 plus 6 plus 8 plus 10. So instead of having written out this series with all of these terms, adding them together, this compact way using sigma tells us exactly the same thing. Let's look at one more example and then make it a little bit more complicated in this example. This time I'm going to look at k going from 1 to 25, so considerably more terms, and my generator looks like this, 3k minus 2. So if I start looking at some of the terms, they're going to look like this. The value of our lower boundary is 1. So I have 3 times 1 minus 2. Now all of that is my first term, and I'm going to write that down here so I can really see what it looks like. 3 times 1 is 3, minus 2 is 1, plus, the second term is going to be 3 times 2, so it goes up by 1. So 3 times 2 minus 2. So we have 6 minus 2, so I have a 4. Plus, and I could continue along like this, and I'll do a couple more here. So plus 3 times, and the next value for k is 3, minus 2. So we're going to get 9 minus 2, or 7. Plus, now I'm going to keep going like this, obviously, but I'm not going to write out all of these terms. That would be too time consuming, and I sure don't have the room. So plus what? Well, the last term will have a k value of 25. So it's going to be 3 times 25 minus 2. So that 75 minus 2 is 73. So I could express a lot more terms, and by putting in a dot, 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 it saves me having to write it all out. So this is what the series is that we're talking about. Now suppose somebody said, evaluate. Okay, so what does evaluate mean? Well, evaluate means that I want to figure out what number it's all equal to. In other words, what is the sum of all of this stuff here? So let's see if we can figure out some way now of answering that. If we look at the series that has been produced, once I've expanded out the sigma notation, if I look at this particular series here, I look at it and I say, hey, this looks arithmetic. And in so doing, all I need is the value of a, which is 1. I need the common difference, which is 3. And I need the number of terms. How many terms do I have? Well, 1 to 25, including the 1 and the 25. If we count this up, we will find that there are 25 terms. But let me show you a little trick, because sometimes it's not so obvious. Sometimes we don't start with 1, in which case there wouldn't have been 25 terms. Supposing, for example, I started with 4 or something. How do I find out the number of terms without counting them out on my fingers? The technique is to find n, we take the upper limit, 25, subtract the lower boundary, and add 1. And the number you get is exactly how many terms. So in this case, 25 minus 1, okay, plus 1 turns out to be 25. Okay. And I have another thing that's very handy here, which is my last term. And so because I know my last term is 73, I might be able to avoid using the longer formula for finding the sum of an arithmetic series. I'm going to use the shorthand formula, which would look like this. The sum of 25 terms, well, that'll be n over 2 times my first term plus my last term. And if you know the last term, this is a kind of a shorthand formula to use. Now, I worked this out ahead of time, and I'll let you confirm that, but I believe you'll find 925 is the answer of this series when we evaluate it. So, what does that tell me? Well, this is the shorthand sigma way of writing that, and if I had to evaluate what this equals, well, I'd know it equals 925. Okay, so we've seen a couple of examples where we start with sigma notation, we expand it out, maybe we evaluate, maybe we just look at what kind of a series it is, but what about working the other way? What if in the next example I start with the expanded form and said, well, here's a series, can you please write that for me using sigma notation? Let's have a look what I'm talking about. First we'll clear off this board space and then have a look. Okay, just about there. Okay, so what I'm talking about is something like this. Suppose we had 3 minus 6 plus 12 minus and so on, and we decided that our last term would be 192. Now that's a very reasonable series here. We'd have to look at it and decide, first of all, what kind of a series is this? Sometimes you can identify them, how you generate each term very simply, very directly, and then put it into a sigma form. Sometimes it's helpful to look at it and say, this thing looks to me like it's some kind of a geometric series, and I can say that A is 3, and I can see that R looks like I'm multiplying by negative 2 each time, and all I need to do is figure out how many terms I have. Well, I have a term generator for geometric series, and that might be helpful to us for putting this all ultimately into sigma format. What I'm going to do is say, well, the term generator looks like this. A times R to the n minus 1. And this generator looks very good, except that I don't know how many terms. I know the last term has got a value of 192. Maybe that can be helpful. 192 is the value of the term, and it would be A, which is 3, times R, which is negative 2, raised to the n minus 1. So if I solve this now for n, I'm going to know how many terms. I mean, is this the 10th term, or the 8th term, or the 50th term? So that's what this is going to tell me. So I'm going to go ahead and do a little solving here. Now, the way I decided to do this was to keep it pretty simple. If I divide by 3, I'm going to get 64, and then that would equal negative 2 raised to the n minus 1. And I could get in and do some logarithms and bring down the n minus 1. But in this case, I think I might be able to just spot it simpler by saying negative 2 raised to the 6th is the same as 64. And now that it's base 2, which is the same as the right side of my equation, then I know that 6, this exponent here, must equal this exponent here. So I know that n is a value of 7. So how does that help me now with expressing everything in terms of sigma? Well, let me just make a little board space here. And I guess since I sort of need some of this stuff up here, I'm going to erase this work here. And just remember that n is equal to 7. So that's what I'm going to do. Sort of hate to see this hard work disappear, but I need the room. So n is equal to 7. So that's what we figured out with the work that I just erased. So how do I write this in terms of sigma? Well, here's what we got. Now I'm going to use k again. It doesn't have to be k. I'm going to start with 1. And I believe that since this is the 7th term, that there are 1, 2, 3, 4, 5, 6, 7 terms. So I'm going to end with 7. And my generator is going to follow this format here. It's going to be 3 times -2 raised. And this time I have to change from using n to using what my counter says, which is k minus 1. And so I believe that this will now generate this particular series up here. As I say, sometimes you don't have to identify what kind of a series it was. In closing here with one simple example, let me show you one that wouldn't involve any fancy stuff at all. Sometimes you just look at it and you say, hey, I know what that is. What are we talking about if we're saying that? Well, we might be saying something like this. You might have a series that looks like this. 1 plus 4 plus 9 plus, and we'll just keep it simple. Say we went up to 49. If I was going to write this with sigma, well, it doesn't look arithmetic and it doesn't look geometric, but I might be able to just say, wait a minute. If k started with 1 and went up to 7, and I just took k and squared it, well, gosh darn it, that's that particular series. So sometimes they're arithmetically based, sometimes they're geometrically based, and sometimes they're neither. Anyway, that's the world of sigma notation. Pretty handy stuff, I'd have to say. We'll catch you later.